Hi, I'm Zach.
Hi, I'm Uma.
Together, we will present some related results from my paper with Bill Fefferman, Eliminating Intermediate Measurements in Spacebound and Quantum Computation.
And I will be talking about a joint work with Ran Ras and Zhan on a quantum log space algorithm for powering matrices with bounded norm.
Let's start by talking about the principle of deferred measurement. Suppose we have a single qubit in the zero state, and we apply this simple circuit to it, which consists of a Hadamard gate, followed by a measurement in the computational basis, followed by another Hadamard gate, followed by another measurement in the computational basis. It's easy to see that the result of the first measurement will be 0 with probability 1/2 and 1 with probability 1/2. And then the result of the second measurement will also be 0 or 1 with equal probability. The principle of deferred measurement tells us that it's sufficient to only perform a single quantum measurement at the very end of a computation. We can get rid of any intermediate measurements. Now, of course, this does not mean that we could just take the first measurement gate in our example here and rip it out of the circuit, because if we did, then we end up with this circuit here, where now the result of the single remaining measurement is always 0. And so these two circuits have different output distributions. They are not equivalent. Instead, the principle of deferred measurement works by simulating a measurement using a fresh qubit and a CNOT gate. It's then easy to check that the output distribution of this new circuit is identical to the output distribution of the original circuit. These two circuits are equivalent. Now, if we only care about the amount of time that a quantum algorithm uses, then this procedure is great, as replacing each intermediate measurement with a CNOT onto a fresh qubit does not increase the running time. However, if we also care about the amount of space that is used, then this procedure is terrible, because we need one fresh qubit, that is one additional unit of space, for each intermediate measurement. For example, consider a quantum algorithm that uses Logspace and polytime and is allowed to make intermediate measurements. Now, in polytime, we could make polynomially many intermediate measurements. And so if we want to use this procedure to eliminate all of those measurements, we would need polyspace, which is an exponential blowup of the amount of needed space, which is extremely not good. And so the natural question, which has been considered by a whole collection of previous papers, is, can we eliminate intermediate measurements without a space blowup? Our first main result answers this question. It is possible to eliminate intermediate measurements with neither a space blowup nor a time blowup. As our second main result, we give new quantum log space algorithms and matching hardness results for a collection of natural linear algebraic problems. In particular, for a well-conditioned matrix A, we consider approximating the determinant of A, or the inverse of A, or A raised to some high power, and other such similar problems. By combining our algorithms and matching hardness results, we show that all of these problems are complete for quantum log space. Moreover, this second result is actually the key tool that we use in our proof of the first result about intermediate measurements. But before we delve into the details of these results, let me first spend a minute trying to convince you that space actually matters in quantum computation. Now, after several decades of progress, experimental quantum computers have advanced to the point where we are now in what John Preskill calls the noisy intermediate scale era of quantum computation, where intermediate scale refers to the fact that these quantum computers have few qubits. For example, consider a current state-of-the-art quantum computer, IBM's Q system, which has 53 qubits. To put that number in perspective, we can compare this state-of-the-art quantum computer with a not at all state-of-the-art classical computer, Apple's iPhone 7, which has 128 gigabytes of memory and has a retail cost of something like $400. Now, I don't know exactly how much IBM's Q system costs to build. I just some sort of trade secret, but I think we can safely assume it's a great deal more than $400. Of course, this is a somewhat unfair comparison, because when one says the iPhone 7 has 128 gigabytes of memory, that is conflating together multiple different kinds of memory. But the basic message is true. Current and near-term quantum computers have few qubits. They have a small amount of quantum memory. And so space really is important in quantum computation. Next, let's discuss why we actually care about eliminating intermediate measurements. Firstly, quantum measurements are a natural resource, just like time and space are, and so it's desirable to minimize our use of this resource. Secondly, unitary computation is reversible, and reversible computation is desirable for a whole host of reasons. The ability to undo a computation by running that computation in reverse is routinely used in both the design and analysis of quantum algorithms. For example, the tidy subroutine calling procedure or the quantum rewinding technique. Moreover, reversible computation does not generate any heat, which is of practical relevance. Lastly, the fact that we can eliminate intermediate measurements without a space blowup shows that the definition of quantum space is robust. That is to say, the class of languages recognizable by a quantum computer in a particular spacebound is the same whether or not intermediate measurements are allowed. In particular, consider the relationship between probabilistic space and quantum space. Now, it's easy to see that with intermediate measurements, quantum space can just directly simulate probabilistic space. On the other hand, before our result, it was not known if probabilistic space was contained in unitary quantum space, which was a rather peculiar state of affairs, as quantum computation should generalize probabilistic computation. Of course, now that we can prove that general and unitary quantum space are equal, we can conclude that probabilistic space is indeed contained in unitary quantum space, as we would expect. Next, Uma will present definitions of the relevant models of space-bounded computation.
I'll begin by introducing our models of space-bounded computation. These will be relevant to both parts of the talk. I will then focus on results specific to our work with Zhan and Wei. Our model of space-bounded computation is as follows. We have S registers initialized to the all-zero state. These registers can be quantum or classical, depending on the model, which I will specify later. At each time step, we update the memory. This goes on for time which is at most exponential in S. Finally, we declare the contents of the first few registers as the output of the algorithm. How does the input enter the picture? Well, the input is what decides these update operations. We require that there is a classical deterministic space S Turing machine, which on input X outputs a description of these update operations. We say that an algorithm computes a function if the output of the algorithm agrees with the value of the function on input X. If the algorithm is randomized or quantum, we require this to happen with probability at least 2/3. Now let us see what kind of update operations we allow and what are the different models of computation that arise as a result. We'll be interested in Logspace algorithms, that is algorithms which use space which is logarithmic in n and time polynomial in n, where n is the length of the input x. We can think of classical Logspace algorithms, that is the class L, as algorithms in this framework where the updates are deterministic transition matrices. We can think of PPL in this framework where the updates are stochastic matrices. For quantum Logspace algorithms, we get different models depending on what operations we allow. The first is unitary quantum algorithms, that is BQUL. These algorithms have quantum memory, that is, they can store qubits, and their updates are by unitary quantum channels, That is, you can apply unitary quantum operations. Since we want the output to be classical, we measure some registers at the very end of the computation and declare the measurement outcome as the output of the algorithm. Note that in this model, we can measure the qubits only at the very end of the computation when we're ready to declare the output. This naturally leads us to define a model BQQL, where we can also do measurements during computation. More generally, the updates are by unital quantum channels. Finally, we have general quantum log space algorithms, where the updates are by general quantum channels. Let us see a different way of looking at these quantum log space algorithms. We can think of unitary quantum log space algorithms as algorithms which apply unitary operations. We can think of PQQL algorithms as algorithms which, in addition to performing unitary operations, can also perform intermediate measurements. Finally, we have general quantum log space algorithms. These algorithms can, in addition to performing unitary operations and intermediate measurements, they can reset qubits. They can take any qubit, discard it, and get a fresh qubit initialized to the ket 0 state. This has the effect of resetting that qubit. General quantum log space algorithms can also perform this operation. This is a different way to look at these quantum log space classes. There is another way to look at them. We can think of unitary log space algorithms as algorithms which have purely quantum memory and perform only unitary operations. We can think of pure quantum log space algorithms as algorithms which have only quantum memory, can perform unitary operations as well as intermediate measurements. Finally, we can think of general quantum log space algorithms as algorithms which have both quantum and classical memory. On the quantum memory, they can perform unitary operations and measurements, and they can also copy the measurement outcome onto the classical memory. This is a different way of looking at quantum log space classes. I'm now ready to state our main result. Our main result is a unitary quantum log space algorithm for the contraction matrix powering problem. In this problem, we're given an n by n real contraction matrix, that is a matrix with spectral norm at most 1. We're given parameters t is at most polynomial in n, epsilon which is at least inverse polynomial in n, and indices s and t. Our goal is to estimate the s, tth entry of a to the power t up to epsilon additive error. In other words, we want to approximate the entries of powers of contraction matrices. We show that this problem can be solved in the unitary quantum log space. By a simple reduction, we can also solve the iterated contraction matrix multiplication problem in unitary quantum log space. In this problem, we're given t different contraction matrices, and we want to estimate the entries of their product. This is equivalent to the contraction matrix powering problem. The matrix powering problem is a very fundamental problem in complexity theory. It says a lot about the structure of space-bounded computation. We don't know if the matrix powering problem can be solved in classical log space. In particular, the best algorithms for contraction matrix powering that are classical seem to require either super logarithmic space or super polynomial time. The contraction matrix powering problem has consequences to the problem of eliminating intermediate measurements from space-bounded computation. Zach has already introduced this problem and told us how it is a fundamental problem in understanding quantum space-bounded computation. We show that BQUL equals BQQL. That is, quantum log space algorithms, which can perform unitary operations and intermediate measurements, are no more powerful than quantum log space algorithms, which can perform only unitary operations and measure at the very end of computation. In other words, measurements during computation don't give more power to quantum log space algorithms with only quantum memory. More generally, we show that any pure quantum algorithm of space S and time t with intermediate measurements can be simulated by an algorithm without intermediate measurements, where the space overhead is plus log t and the time overhead is polynomial in 2 to the s. In particular, we give a principle of deferred measurements that works for space-bounded algorithms. At this point, I should mention the result of Fefferman and Remscrim. They show that BQUL equals BQL. In other words, the ability to perform intermediate measurements or reset qubits doesn't give more power to space-bounded quantum algorithms. Let us see how this affects the picture of space-bounded computation. We have the class L, which is deterministic log space algorithms. When you give it the power of randomness, what you get is BPL. We have that L is contained in BQUL. It can be shown that BQQL is what you get when you give BQUL the power of randomness. Earlier, I had defined it in terms of the power of intermediate measurements, but this is equivalent to the power of randomness. In other words, we can think of BQQL as the randomized version of BQUL. In other words, our result can be thought of as a derandomization of BQQL. The derandomization of BPL is a wide open question. So this suggests the power of quantum in the sense that it can reversibly toss random coins, so to speak. Of course, now we know that BQUL equals BQL. That is, quantum log space algorithms don't need random bits or the ability to reset qubits. We also make partial progress on the question of BPL versus BQUL. It was not known whether BPL is contained in BQUL. Our result is able to handle the aspect of randomness of BPL, but we're not able to handle the aspect of resetting qubits. Of course, now we know that BQUL equals BQL, and hence BPL is contained in BQUL. In the next minute or so, I will try to describe a high-level overview of our algorithm for contraction matrix powering. Our algorithm is as follows. The first step is to embed each of the contraction matrices inside a unitary matrix which has a small log space quantum circuit. In other words, we embed each of these contraction matrices inside a unitary log space quantum circuit. Our second step is to compose these quantum circuits carefully so that if we have an embedding of A and another embedding of B, then what we get is an embedding of A times B. This allows us to get an embedding of the product of contraction matrices. Finally, given an embedding of the product of contraction matrices, we show how to estimate the entries of the product of these contraction matrices. This uses an argument similar to Grover's search. I hope I've given you an idea about the kind of techniques that go into our work. Now Zach will tell us about his results with Bill Fefferman.
Let's start by talking about the matrix inversion problem. Here, we're given an n by n matrix, A, and a pair of indices, I and j. The goal is to approximate the ij entry of A inverse to inverse polynomial precision. How hard is this problem? Well, the crucial parameter is the condition number, kappa of A, which is defined as the ratio of the largest singular value of A to its smallest singular value. Roughly speaking, if the condition number is very large, then even a small change in the matrix A can cause a very large change in A inverse, thereby making the approximation problem for A inverse harder. We want to focus on the easier case, when A is well conditioned, meaning that its condition number is not too large. In particular, suppose that A is polyconditioned. Then, as Hauer-Hassidim and Lloyd showed, for a somewhat different setting of parameters, namely sparse exponentially large matrices, this problem is in BQP. Then, building on the original poly-time Hauer-Hassidim and Lloyd algorithm, Toshma showed that well-conditioned matrix inversion for n by n matrices is in BQL. This result was improved by Fefferman and Lange, who gave a BQUL algorithm for this problem, and also proved matching hardness results, thereby showing that well-conditioned matrix inversion is BQUL complete. We extend this result even further, and show that well-conditioned versions of other natural linear-algebraic problems are also BQUL complete. To do this, let's consider the determinant problem. Following Cook's original definition, the complexity class det consists of all problems reducible to computing the determinant of an n by n integer value matrix. Where, to be clear, we're now considering computing the determinant exactly. This class has many natural complete problems. Of course, by definition, determinant is complete for this class, but also so is the problem of exactly computing the solution to the integer-valued matrix inversion problem, matrix powering problem, and other natural linear algebraic problems. Now, as we just mentioned, Fefferman and Lange show that the approximation problem for polyconditioned matrix inversion is BQUL complete. We generalize this and show that the polyconditioned version of all the standard dead-complete problems are BQUL complete. In particular, this will then imply the fully general version of our eliminating intermediate measurement result. Now, we note that reductions between the various dead-complete problems are well known. However, these reductions generally do not preserve the property of being well conditioned, and so we will have to exhibit reductions which are more exotic. However, we first consider an easy case where a simple reduction is possible. The well-conditioned matrix powering problem. This is a generalization of the contraction matrix powering problem that Uma discussed earlier. As before, we consider approximating a single entry of some polynomially large power of the matrix A. The only difference is that we can now work with a weaker promise. Namely, in contraction matrix powering, the norm of A was required to be at most 1. Now, we only require that the norms of all the powers of A are polynomially bounded. Now, there's a very simple reduction from this problem to polyconditioned matrix inversion. Of course, as this matrix inversion problem has already been shown to be in BQUL, we then immediately conclude that this matrix powering problem is also in BQUL. The reduction uses the following matrix B. This is a block matrix where each of the blocks are n by n. The blocks along the main diagonal are all given by the identity matrix, and then immediately above the main diagonal we have copies of negative A. The rest of the matrix is all zeros. It's then easy to check that B inverse has a very nice form. Namely, along the main diagonal, we have copies of the identity matrix. Immediately above that, we have copies of A, then A squared, then A cubed, and so on. Therefore, by sizing the original matrix B appropriately, A to the T will appear in the top right corner of B inverse. Moreover, it can be shown that B is polyconditioned, and so we really do have a reduction to polyconditioned matrix inversion. This idea then straightforwardly generalizes to the well-conditioned iterated matrix product problem. This is similar to powering, except now we consider the product of polynomially many potentially different matrices. Using a similar idea, we can also reduce this problem to polyconditioned matrix inversion, and therefore conclude that this problem is also in BQUL. Moreover, this problem can also be shown to be BQL hard. To see this, note that a general quantum circuit is just a sequence of arbitrary quantum channels. Each of these quantum channels corresponds to a single matrix, and applying the entire circuit corresponds to the product of all of those matrices. Moreover, it can be shown that this problem meets our well-conditioned criteria, and so BQL hardness follows. By combining these two previous observations, we then conclude that BQL equals BQUL, which then applies the analogous result for any larger spacebound. Therefore, we have a space-efficient way of eliminating the intermediate measurements in the fully general case. Moreover, we also show results for RQL and NQL. These are the one-sided bounded and unbounded error versions of quantum log space. For example, we show that NQL equals NQUL. Furthermore, we show results for the quantum Merlin-Arthur and one clean qubit versions of BQL, RQL, and NQL, though I'll refer you to the paper for details on all of these results. I will conclude by talking about the well-conditioned determinant problem. Here, we have a polyconditioned matrix A, and we want to approximate the log of the determinant of A to inverse polynomial precision. We can show that this problem is BQL complete. And more generally, we can show that the polyconditioned versions of the other standard dead complete problems are also BQL complete. The difficulty here is that the standard reductions between many of the dead complete problems do not preserve the property of being well conditioned. We exhibit a collection of new reductions which do preserve this property. We make use of a variety of different power series approximation techniques, and we also exploit a quantum algorithm's ability to operate on a very succinct representation of a big piece of data. In order to put our result in the proper context, we note that Boyd, Sarah, Elder, and Maribon have recently shown that well-conditioned determinant is in deterministic space log squared n poly log log n. They also made use of power series approximations, However, quantum algorithms seem to have a large efficiency advantage over deterministic algorithms when operating on large power series, which allows us to put this problem in quantum log space as opposed to deterministic nearly log squared space. Moreover, we have a direct improvement on their result as we put well-conditioned determinant in quantum log space, which is contained in deterministic log squared space. Lastly, we ask if it's possible to improve the dependence on the condition number for these results. If so, that would imply a new best classical upper bound on quantum log space. Thank you for listening.
Thank you for the very nice talk. Now we have time for a few questions. So one question that arrived during the talk was from Zvika Brakersky, who asked, what are exactly the rules that what you want to achieve here? If you are allowed to produce a distribution of circuits rather than a single circuit, then you can use poly-Z twirling, for example.
So I'm not sure what's meant here by a distribution of circuits. Do you mean in the definition of the original space-bounded class?
So I'm guessing this kind of relates to the point that every measurement can be simulated using random coins. So indeed, you can take a quantum circuit with measurements and replace it by a distribution over quantum circuits based on the outcomes of these random coin tosses. But we want to avoid that. So it's like drawing the distinction between BPL and L. We don't want to take a distribution over circuits for various reasons. For example, it's not clear how to do error reduction and things like that. You want to take a circuit and apply its inverse and so on. And these kind of operations are really useful. And it's not clear how to do this when you have a distribution over circuits. Yeah, I'm happy to answer this in more detail in the roundtable, maybe.
Yeah. I have another question that came to me. So this matrix A that you work with, how is it given? Is it like every entry is written down in a classical memory, or what is the input exactly?
So if you're referring to this sort of collection of different linear algebraic problems like matrix powering and so forth, then we're imagining that the input problem has some classical description. So say a classic circuit describes the particular matrix or collection of matrices.
So it's not that like every matrix element is written down, but rather there is some short circuit generating the matrix entries, like a white box oracle or something?
Well, in the real parameters of interest, I suppose it doesn't matter terribly much, as for say the crucial result for BQL equals BQUL, the matrix is dense in the first place, and so this could just be write down all of the matrices, say to the right number of bits of precision in the first place. There's write down all of the entries of the matrices just directly as a string. But one can also say something in the scaled up setting.
Okay. So there is one more question from Cedric Lin, who asked about whether, so you showed for quantum space-bounded computation with allowing unital channels and allowing generals are equivalent. Can general channels give an advantage over unital channels? For example, when you care about both space and time?
Well, I suppose you could ask a very finely grained question. That is, the way we had defined BQUL and BQQL and ultimately BQL is log space polytime. And so in that regime, no, unital would not have, there'd be no difference. That is, the fully general would have no super polynomial advantage over unital. But you could ask a more finely grained question, which is, for which the answer is unclear to me, but something like a particular spacebound and time bound where the it's not sort of this extreme case where the time is exponential to space, but something sort of smaller, and compare the unital version and the fully general version. Here it's not clear to me if there's the potential for a small advantage in time.
All right, well, we roughly got to the bottom of the questions, at least I think as far as we can answer in this format. So thank you very much for your very nice talk. And